Okay, everybody, welcome back to the last weekend of the, and this is really, they call it the advanced weekend, but it's really the easiest one of all three. Because now that you understand Java, we put it all together and we revisit it a little bit. So starting today, actually, at 9 o'clock a.m., I'm starting to review for the final exam. Final exam is tomorrow at 3 o'clock. So that will be the ultimate test to see if you understand the material. So we will not have a final exam review. So those people who showed up today, right now, you're gonna have the best review because I'm starting the review now, and I have the exam with me. Actually, I can tell you what kinds of questions and stuff are on it. We're gonna spend the morning reviewing, and then we'll spend the afternoon enhancing our skills and looking a little bit more at examples, and then tomorrow at about 3 o'clock we'll have the exam. So this is your review for the final exam, and so I'm not going to break off later on and have a separate review. Instead, I'm going to spend all day today in review. So good morning. So for those of you who just came in, we are starting our review for the final exam all day today. So for those people who showed up now, you're going to get the review. For those other people, you're going to have no idea what's going on. So anyway, if you're interested in this review lectures that I'm going to go over, there's about 20 of them or so, and they are in, if you go back to the main directory out here, or main forum I should say, if you go into the Object-Oriented Programming with Java and go into the Programming Tutorials, I've got source code examples and I've got some PDF lectures that I'm going to go through. We're going to start with day 1, and we're going to go through at the speed of light. By the end of the day, we'll cover everything there is to know about Java for the exam, actually. Because it's hard to take a programming language and talk about an exam for it without reviewing it, without going over it. So today's not going to be boring, however. Hopefully it's your opportunity to ask questions in terms of some of the content or concepts you may not necessarily be comfortable with. But here are the sources of all of the materials I'm going to go over today, as well as all of the source code examples. Not very much this weekend on Android, it's all on Java. So we have a couple fun little tutorials we might do in the afternoon, but for the most part, it's all on Java programming. It's object-oriented programming in Java. So, all right, so this one here is Basics 1. If you, I shouldn't have closed that window. If you go into here, and you go into Object-Oriented Programming with Java, and you go down into the Programming Tutorials link. This is what we're looking at here, Basics 1 and Basics 2, and Syntax, which I'm going to cover for this first part of it. And so we'll go down memory lane from day 1 and kind of just review through and iterate points. Because sometimes, you know, when you hear it one more time, it solidifies everything for you, hopefully. So I'm going to start out again kind of looking at the differences between C++ and Java and other languages as well that fit into the object-oriented realm, revisit the concept of the object, and look at the instances and class variables and going kind of quickly in terms of the concepts. Some people call Java more object-oriented than C++, if you think about it. It is, actually, because you can program in C++ without object orientation. So similarities are used in the syntax and the building, which is why I didn't spend too much time in the beginning going over the syntax, assuming that you've had some sort of programming experience in the past. The syntax is extremely similar to C and C++. We do have some differences. The methods or member functions are only function type that is being used. Objects is the topmost ancestors for all classes, which we don't have in C++, actually. In purposes of what you need to know for this class, you don't have to know anything about C# or C++. It's all on Java. We have the user-defined classes that are used like built-in types in C++, also in Java as well. So the differences from, as well, all methods use runtime, not compile time. So everything's dynamic in Java versus static. These are just some general characteristics of the language, just to get ourselves back into Java here. Types of the objects are known at runtime, and all objects are allocated on the heap in Java. There's no static anything. So C++ is really a static language. So we use the dynamic features of Java in Android because it's all created when the app is running. When the when the objects are being created, the memory is being allocated and deallocated, and it's actually being controlled by the JVM, if we remember that. We have a separate JVM for the Android platform, the DVM, which runs a very similar concept, actually. In comparison to C Sharp is very similar to Java in object orientation, but it's also very similar to C++ as well. So. Alright, so from day one we learned that we had the class, and the class represented the object. So the exam that you're going to get tomorrow is about 25-30 questions of multiple choice, and it's going to go through all the concepts I'm reviewing today, starting with this lecture actually. So what we're looking at is, what is the object in terms of object orientation, and the object itself is the class. So it's the implementation of the class. So class means a category of things or objects. So the class itself can be used in Java as a type of field or local variables, or as a return type of a function or a method. So the object means a particular item that belongs to a class. It's an instance of a class, if you think about the class as a template. And here's an example. We have string 1, or string S1, which equals hello. So here the string is the class, and the variable S1, and the value hello, or objects or instances of the string class. Everything is an object in object orientation. Everything is an object in Java. So if you had a question that said, a multiple choice question or something that said, what is S1? And one of the answers said, well, it's an instance of an object. All right, it's S1 and the variable hello are objects, or instances of the string class. That would be the correct answer. If you said that S1 was a variable, that'd be wrong, actually. It's not a variable. So we have built-in variables in the language: integers, floats, doubles. Those are usually referred to as primitive data types. These are not, the string is an object, actually. And all other objects that you would create, pencil, employee, those are objects. They're not primitive data types. They're not variables. So variables we don't actually have. We have what's called data members. So let's go into the concept of instance variables. So we have two varieties of these. We have class variables and instance variables. By definition, if we talk about the instance variables for a second, the data that is stored inside of the object belongs to the objects. So the instances of the objects, those are instance variables. Also called data members or fields. I refer to them in some of the lectures as fields. In fact, that's how we started out. If you remember the first day of the first weekend of this course, we started out talking about fields and things of that nature. We have the syntax, wrote the general syntax here, where we have public, keyword public, meaning that these data members or fields or variables can be seen outside of the class in terms of being able to be assigned values outside of the implementation of the class. So out in main, if something was public and we used some data type for it, and we had field 1 and field 2, field 1 and field 2 would be accessible. So you want to know the differences between public, private, and protected in terms of how that's being used. And these are access methods, to review the point. Access methods tells us how we're going to be able to access it. So in any class that also has methods, it's almost always better to declare those instance variables, these here, as private, not public, as the little blue note says on the side here, and have the member functions public. So as in all other object-oriented programming languages, we want to keep those data members private and then make the member functions public so that we can access them and enforce some rules, so we're not just randomly changing values of variables and stuff. We're making some logical, correct choices, hopefully, for those values. So in terms of the motivation, let an object have the persistent values. It's often said to be object-oriented programming. So objects have 3 characteristics to them, as I mentioned before, and this is also another question on the exam, actually. What are the 3 characteristics of an object? Object has a identity, state, and behavior, actually. In terms of object orientation, well, what's the identity? Well, it's usually the name of the object, and it has something to do with its hierarchy normally. If it's an object of a shape, object of a circle, square, that's usually is referred to as its identity. And then what are the states and behaviors? Well, the states are normally associated with the instance variables or fields. So that's the data that were being held for the object. So a state would be representing, is the elevator, which floor is the elevator on? Is the elevator running or is the elevator stopped? And then the behaviors. If I were looking at an elevator class, the behaviors would be move elevator up, move elevator down, stop elevator, start elevator. So the behaviors are controlling the states because the behaviors are changing those state variables of that data. So those are the three components of an object in terms of its object-oriented scenario. And then we have some examples here. We have a ship example where we have instance variables, and here's ship1.java and test1.java. And then you're going to go, well, where are these from? Well, if we go back out to that website and we take a look, oops, I probably should have just bookmarked it, at those, and this is a good kind of, I'll do this for the first couple of examples here, and then we'll just assume where everything's going to be located at the same location in this programming tutorials here. If you download this file here, it's a jp.basics.zip, and if you take that file and open it up, you'll see a bunch of examples, and this one happens to be called ship1, and it's right down here actually, ship1.java. And then we have test1.java that goes along with it right here. If I load it up into Eclipse, I can see a graphical version of it, or I've just basically loaded up my terminal window, and I can type them out in here. As an example, if we look at this, or I can double click on it and see it in Xcode, which is going to give me a little bit more colorful representation. So if I look at ship1 and open it up, here it is. I see something that looks like this guy here, ship1. So this is where these examples are coming from. So they're labeled ship1, and then we have test1, which is going to be this other one over here. So in a matter of making the examples, here's test1. Test1 is going to make a couple ships here, and we can see the ships over here. So if you want to see it live, go ahead and use the source code examples. Otherwise, I'm going to refer to them here. So that's where that's coming from. It's nice, especially if you're still having problems with the concepts, haven't done the assignments yet. Well, you guys probably aren't because you're here, but the people that aren't here are going to stroll in for the final exam review and then realize they missed it because I started with day one with it. So those are the ones who are going to really probably use this information the most. But long story short, that's what I'm referring to here. So if we take a look at these examples here and go back to ship1, instance variables here, they're public. So the design of this ship1 is not necessarily the most ideal because the data is public. And remember, I just said a few minutes ago I should make that data private. But it's illustrating a point here. If we said, as an example down here in the test1 program, this is the main driver. So we have instances of classes that we create. So we create objects that have an identity, state, and a behavior, and we hold that information inside of those objects, and then in the main program we create instances of those objects, if you remember that. And here's test1. Why do we call it test1? I don't know, we could have called it like my program. So why do we call this ship1? Well, because it's a ship. We're putting a ship inside of it. So we're going to call this, and this is also another trivia question that's on the exam. You name the objects with a capital, actually. And that's the name of the object. So if I were writing a ship1.java, if I were writing a ship1 class, it would go in a file called ship1.java. That's important, actually. In fact, it's required. If you don't do that, the program's not going to compile. Does this matter? Yeah, it does matter. If I call it test1, I have to put it into a class called test1. I don't have to call it test1. I can call it anything I want. It's just the same way I don't have to call this ship1. I can call it ship if I wanted to. But hopefully you understand the point. So the name of the class always matches the name of the object that's inside of the class. We only put one object inside of one class file, and we keep it separated out that way. That way we can include them into the project, or better yet, we don't even have to do it. Just put it in the same path or directory structure, and then make an instance of it inside of the class. So here we have test1, and inside of test1 we're making a new ship. So ship1 space s1 is equal to new ship, which is what we've got going on here. And then ship1 s1.x and x1.y. Well, where do we get that from? Well, we're getting it from the double x and the double y up here. And then we have speed and direction that are also coming out of that as well. So anyway, it kind of gives you an example of using the data with the dot notation inside of the driver program that we're looking at here. And then we have our name here. And then noticing at the top, we don't have any includes because we're going to use imports, but we don't necessarily are going to import anything because it's all in the same scope, this particular example. So, and then this is a continuation of the test1. So if you open up the live test1 file and run it, you'll see essentially the concept in terms of using it. And to compile it, you basically run the javac on the command, save it, compile it. You can do it in Eclipse. You can do it on a command prompt. If you're doing a command prompt, you're typing in javac space test1.java to run it, and then running it by going java space test1. Then we have ship1. This is the output. It's going to be ship1 is that location because we're keeping an x and a y. And then, so if we come up and look at the code here, we have the implementation of nothing more than just the hard coding of the x and the y that's associated with the ship. We have a speed and a direction variable that we're using as a variable. So this one isn't really using, because we have the speed here we're setting, the direction here we're setting, and then we have a ship name that we're setting for it. So, and then we're calculating out this information here without using any method calls. So this particular example is really a bad one because we're not using methods. we're taking all this code and we're sticking it inside of the main driver program. And this is pretty big. If you look at the implementation of test1, it's pretty big. So in a better way of doing this is you make the data private, you make member functions, and you stick all that stuff inside the member functions. And so now you can, instead of hard coding or hard setting a value, you can calculate the distance and you can calculate the speed. And you can use a little bit more functionality in that. So major points here, the naming conventions I went through before a few minutes ago, the format of the class definitions, creating class with a new. We use the new out here. So just as a review of that concept as well, ships1, ship s1 is going to be equal to new ship. So using the new syntax here. And remembering it varies a little bit. It's the same concept as C++ though, same syntax. So accessing the fields with the dot notation. So we have the variable name dot field name. It goes along with that as well. So Java naming conventions, as we saw before, we start out with a class that has an upper. So I still get, in fact, I still saw some files actually sent to me. Someone said, "Hey, is this okay?" I looked at it and went, "Well, do you really even know what you're doing? Because you have a lowercase, you have to capitalize. If it's an object, you want to capitalize it." And then when they, put it in a class and they called the file something else, and then I'm like, "Well, this is not even going to compile," and it's like, that's a red flag right there. So if you want, when you're turning in those assignments from the first 2 weeks or whatever, actually there's 6 of them total. When you're submitting them, keep in mind you're giving yourself red flags when you start putting them in a Word file or you start changing the name of the class file or something, and it's not capitalized and it doesn't even match the name of the file you put it inside of, and it's all kind of jumbled. That's like a dead giveaway that you probably didn't write yourself or you probably don't know what you're doing, kind of thing. So. You want to start classes with upper letters, and the constructors that we're going to discuss in a few minutes have exactly the same name, and they match it identically, also with upper letters. Here's some other naming convention things. So start other things with lowercase letters. So instance variables, local variables, methods, parameters, everything else is lowercase. So just the class name is uppercase. That way you can always remember if you're making an instance of a class because you're using an uppercase object. So string in the language is capitalized, float's not, or integer's not, because those aren't objects. Those are primitive data types. But the name here of the variable that we're using with the object is lowercase. So string name is going to be equal to something. So objects and references. So as I mentioned before in our little review, we had objects that are instances of classes that are created, and now we have this concept of the reference, which isn't really the object, it's the reference to the object. So although we don't have pointers in the Java language, we have references, and we're using pointers actually, because we're using new and delete. Actually, we're not using delete, we're just using new. And references. So once a class is defined, you can declare variables or object references of that. So we have ship S1 and ship S2. We haven't allocated any objects though. We just created references to them. Or point start or color blue, which are reference variables. So object references are initialized to null. They don't actually point to anything. So the null value is a distinct type of Java that is not equal to 0. Primitive data types is an example. Int cannot be casted to an object string either, but there are some conversion wrappers that are associated with it. So the new operator is required to explicitly create the object that is referenced here. So we have new that's going on here as well. So this is all review, by the way, for those people who just showed up. So see, accessing instance variables. So we use the dot notation if we remember that. And then as an example here, we're going to use the built-in class point that has an x and a y. So we have point p is equal to new point, and we're going to give it 2 points, so 2, 3 for the x and the y. And then we're going to go through and do some calculations on it by referring to it as p.x and p.y, which are essentially going to be our two variables. So we use the dot notation for that, and these are referred to as instance variables because they belong to instances that are created of classes. We have some exceptions here. We can't access fields in current object without the variable name. We're going to see something coming up here where we're going to look at the class versus instance concept. It's also conventional to make all of the instances variables private, as mentioned before. So if we're going to make them private, we're going to need to create methods, and those methods are the functions. So they're really called methods or messages by definition. Methods can also be called member functions. C++ textbooks normally call them member functions and data members, member functions. Java, a little bit looser, there's like 3 different names for it. If you're following true object orientation, they're messages. If not, they're methods. So methods are a way of adjusting or modifying data members, fields or variables, however you want to call that. Here's your syntax where we've got the keyword public. Are you ever going to have a private? Can you make them private? Sure, why not? But what's the sense of making them private? Well, maybe it's only going to be used inside of the class. So if you want to make it usable outside of the class, you're going to make them public. Public class, my class, and then it's going to return. We're going to have a return type associated with it. It's going to return something, maybe. Who knows? It depends on what we're going to do with it. So the motivation here is we have the class definition, my class, and then we have a method that's inside of my class. So it's actually inside of the opening and closing brackets that are associated with the definition of the class, which is different than Objective-C, actually, and different than other, similar to C++, actually. So the methods are defined and the data is defined inside of the class implementation. There is no implementation or interface or specification. There's just one file. So Java's got just one file. There's no such thing as a function prototype in there, but there can be depending upon how you're going to do it. Usually you're just going to have the implementation. So you don't have to worry about like the separate .h versus the .c++ or the .m or the .h. So it's all .java. The motivation of creating the methods and the messages is let the object calculate the values and do the operations itself rather than hard coding them and setting them. So methods are the behaviors or the calculations, if you want to think of them that way. So it's often said that in object orientation, objects have 3 characteristics. Well, we went over this already. This one is the behavior characteristic. So the identity is the name of the class, the states are those data members, and these are the methods or the behaviors. So if we rewrite the ship example number 1 and we make it a little bit more functional, a little bit, sometimes make it a little bit more standard, we call it ship 2. So if you go out to the that folder and find ship2.java, you'll be looking at this one here. This one here still doesn't have the data private yet. We still left it public, but we have some private and some public methods that are in here. So unlike C++ where we group it all together, or Objective-C actually, where we group it all together in public and private, instead we just use the keyword in front, the access keyword in front of the name of the method or the name of the variable. So here we have public double x, y, speed. So this is the same pretty much as before in the previous example. Then we have a private degrees to radians, which is a method that's going to be used inside of the implementation but not outside. And then we have a public void move and a public void print location. So if we had this is for a battleship game, by the way. So if we had a ship that was out there, we could move it, we could get its location using the public public methods that are associated with the class. So here's our driver program, and we're calling the methods just like we're calling the data. So we go s1.move, s2.move, so we call it, and then the only difference here is instead of saying, which we haven't really fixed yet, s1.name is equal to ship, well, we're probably not going to do that. Instead, we'll probably create a constructor, which is what we're going to do in a few minutes, that would actually set that value for us. Here, we're using the opening and closing brackets here in the syntax to say that this is a method that we're calling, not setting a name of a variable in terms of a data member. So compiling and running it, so we would go test2.java, test2 to run it, obviously. And we get the same output. So the program itself, and compiling it and running it, kind of trivial. What we're looking at essentially are the upgraded changes we've done. We've introduced some methods. And in this particular example, number 2, we're running the methods now. So the format of the methods and the definitions of the methods accessing the local variables, calling the methods, the static methods, which we are going to get into in a few minutes here. These are not static, these are class level, these are instance level methods and instance level data. This is cool. Made it smaller and bigger by tapping. Huh, interesting. Okay. Actually, I like it bigger. It's good. All right. So then public and private distinctions are made as well. So the basic method declaration here is the return type with the method name and the list of parameters. So we can declare the return type as void. In that case, we're not going to return anything. Same thing as in other languages. Special syntax, that means the method is not going to be returning a value. In such case, we don't need a return. It's just void. So if you didn't notice up here in the implementation of the void method, we're not returning anything. We're just doing some stuff. So there's a lot of people who learn C and they come back and they say, well, everything has to return something. You know, even main returns something. It's like, why are you returning something out of it? It's void. You don't have to return. So reiterating that point. What do we've got here? A couple more examples. We have a method here that's an integer return type, so it's going to return something. We have one here that's a ship, fast ship, so we're going to return a ship. So the return type can actually be the object itself as well. We get that. Makes it more functional. Rather than returning a value that you're going to copy into objects, you're just going to return the object. So here's some examples here. The second one returns a faster of the two ship objects, so we can compare one to the other. And if we did that, we're actually taking in on the command line 2 ships. So this one is a faster method. Method's called faster. So when we run it, we can pass it ship 1 and ship 2 and figure out, well, which one's faster? Well, what's that going to be? Well, it's going to be the value set for speed, because one of them goes faster than the other. So ship1.speed is larger than ship2.speed in this particular case, and then return ship 1 or return ship 2. So in terms of calling methods, the term method means a function associated with an object, and so we have this member function here. So the usual way of calling the member function is to do this, where we've got variable name dot method name, and then we put the method name inside of it. And then, for example, here we have a built-in string class that has a method called toUpperCase. It returns the uppercase method. So string 1, hello, string 2, string 1 dot toUpperCase. So accessing external and internal methods. So as another note here, accessing the methods in another class, in other classes. So you can get the ships that refers to instances of other ships. So ship S is going to be equal to a new ship, and then you can call the method on the object s.move. And then you can access instance variables in the same class. So that you call the method directly, no variables, names, no dots or anything. So you just go move, because there's no instance. So you're just accessing and you're just calling the method that you're running. Here's the other one here. So you can go double D is going to be equal to degrees to radian. So you can actually call the method. So inside of the class, you can call the methods just like they're functions. Outside of the class, you're calling the methods using the dot notation, because you have to refer to the instance that's using the class in order to do that. Two exceptions to requiring a variable name for a method call. So calling the name, the method defined inside of the current class definition, so you can use the method name with the arguments instead of the variable name dot method name. And then returns the methods that are declared static. So you can use a class name. So on static, we're creating what's called a class variable or a class method instead of an instance variable or an instance method. We put the keyword static out there, same use as actually as C++, and at that point we're going to use the class name. If we don't use the class name, we don't know where it's housed, and it doesn't work. And we can never access a static data member or a static method from an instance. That doesn't work either, because the instance doesn't own it, the class does. So we always use the class name dot the name of the method and then the arguments if it's a static method. I have an example coming up actually. So we can call the method of the current class. You don't need the variable name and the dot. As an example here, a ship class might be defined as a method called degrees to radian, and then another function in the same class might do a double angle equals degrees to radian, the direction. So no variable name here and no dot is required in front of the degrees to radian, because it's inside of the class. So if you're inside the class, you just use it just like a method, or just like a function, I should say. So static methods versus instance methods. As I mentioned before, they're run on classes, so you don't run them from an instance. So if I showed you a line of code that said s1 dot something, you know it's not going to be a static. It's not going to be static. It can't be static. It's an instance. S1. Anytime you see a dot notation with an S1, S1 being, if I had previous line of code that said ship S1 like we had seen in these examples, then we're looking at an instance. Instance variables, instance methods all work together. Class works with the class variables, class methods work together. So static functions do not access any non-static methods or fields. So just think static works with static, and non-static works with non-static. So you can't mix and match. You can call static methods or a class name. So you call the class name of the class dot whatever the static function is called, or method. We see one, and we've seen one in examples from the first weekend that said math dot something. That's a static method we're calling, and usually referred to as a function. So math dot cosine or math dot something. When we import the math path package in there, and then we use capital date, capital math, capital something or other. It's a class name, or capital SQL actually. We use that dot something, and we're running it. We're just really using an old-fashioned method, or a static method. So note on the main method, since the system calls main within the first creating of the object, static methods are the only types of methods that main can call directly. So as an example, when building an object and calling methods of that object. So we have static main void. So that's where that static comes into. So method visibility, we have that public, private, protected kind of component going on. We make the methods public. We make the data private, and we use the methods to access the private data. So declaration of the private means that it's outside the methods calling it. Only methods within the same class can access it. Thus the example here, the main method of test2 class could not have done this one here because it doesn't contain it. So attempting to do something that was going to result in a compile time error, if you try to access something that's private from a public perspective, you're not going to be able to do it. This, however, can belong no problem. It can be inside of the class. But if we make the method private, we can only access it inside of the class. Main is outside of the class. Even if you stick it all in the same file, main is outside. It's not inside of the class. If you're going to touch it in main, it has to be public. Just remember that. So only say public for methods that you want to guarantee your class will make variables available to users. So if something is, again, just to reiterate the point, if something is private, not available to users or not available to anything outside of the class implementation. Most people say, well, what is a user? Main's a user. Another class is a user. Anybody who's not inside of the main of the original class where it's defined is a user. It's not like the user, like the end user. It's the user of the class. So you're free to change or eliminate private methods without telling the users of your class either, which is kind of interesting. Because they're private. So private instance variables. So let's take a look here. In the next one, we're going to see almost everything is going to be made private, and we're going to make public methods. So declaring variables inside of methods. So we have data members that belong to the class. Remember, going back to identity, state, and behavior. We also have the concept of variables that can be used inside of methods. If we declare a variable inside of a method, it's inside of the method. It's just like a function. So the scope of that variable is inside the method. So what do? Well, we normally take in variables. If we were creating what's called the setters and the getters, accessors or modifiers for the class, we take the data inside the method, and then it becomes a local variable, not a data member. So we have to assign it to the data member if we want to make that data usable. So if we go type space variable name space equals value, it's hidden. It's not data members that belong to the class, it's variables that are being used inside of the methods. So when you declare a local variable inside of a method, normal declaration looks like this. It looks like the data members, actually. So the value can be a constant, another variable, a method call, something that came in from a parameter that was passed to the method. Constructor invocation, special type of function preferred to as a new. So when we run new, the constructors fire. I'm going to go review constructors in a few minutes as well. Or maybe some special syntax that builds an object without explicitly calling a constructor. Example strings do that. So declaring variables inside of methods, and here's some examples of that where we have integer x is equal to 3 and integer y is equal to x. So special syntax for building the string object, we can say string s1 is equal to hello. String s2 is going to be equal to a new string, goodbye. String 1, string 2, one's going to be equal to the other one. Call a toUpper method on it. So constructors. So Java has constructors, but does not have copy constructors, and it does not have deconstructors. All we have are constructors because the memory is automatically allocated with new, and then garbage collected automatically by the JVM, and which works the same way in the Android system as well. So by definition, all we have are constructors, and the code that gets executed when new is called. So can you call a constructor manually, explicitly? No. You can only do it, it's implied implicitly when you run new. And how does it know which constructor it's going to pick? It's going to be the one that matches the object instantiation format that you're going to give it. So if you say, give me a new pencil, and you just say that, it's going to run the default one. If you say, give me a new pencil, and then set the name to this and the type to this, then it's going to take those two arguments in and set that, hopefully, if you have it created. So there's no law that says you have to create constructors. However, when you start inheriting classes from classes, which is what we're going to get into shortly here, then you're going to need to have some constructors to assign the data if you'd like. Otherwise, you have to do it all manually, which is kind of tedious. Think about it. So syntax here, we have a method that exactly matches the same class name, but it has no return type. Just like other languages, constructors don't have a return type. So public class, my class, and then we have public my class. Our motivation lets you build an instance of a class and assign the values and the instance variables all in one fell swoop. So all in one shot. One shot, you've done it all. So lets you enforce that all instances have certain properties and lets you run the side effects when the class is instantiated. So no user-defined constructor. Here's one. No user-defined constructor. We have public class person1, and this was actually called person1.java. And we have a first name and a last name. And then we have person test. So if we do this one here, person p is equal to new person, we've created it. But what's the value? Well, we're setting it here, but what is really the value of this? First name and last name, it's nothing. It's going to be null, hopefully. In some languages, actually, it's garbage. In C++, it's not automatically set to null. It's garbage. So if you look here at these three lines coming up, you're going to make the property is going to construct a person, so it would be possible for the programmer to build a person and then forget to assign the first name and the last name to it. So if you wanted to, you can set it to unknown or not set or something, which is a more conventional way of doing it. So this is basically demonstrating the point that, well, we've got variables here that aren't set. So constructors, the job of the constructor, to refresh your memory on that, is to assign default values to data so that something is assigned, some meaningful representation of what that's supposed to be. And then we're going to do something with it. So if we create a constructor, we have one right here. This is not a default constructor. This one is a constructor that takes on a initial first name and initial last name. That's going to come through here. And it's going to set whatever we assign to it, it's going to set to those two variables. And in Java, we know we can go this dot first name, but we don't have to because we're inside of a main object class. So we're not doing any supers or thises or anything. We're just essentially just saying first name, well, that's this first name up here. First name is going to be equal to initial first name. Initial first name is going to be passed to it. And down here, we can have a public, and then here's that keyword static, as I mentioned before. So it's a static method, static void main. And in here, we're going to take on, and you know these are command line arguments, I hope. If not, don't worry about it. But we're in here, we're calling person2, which is the name of person2.java. P is going to be equal to new person, Larry, and Page. It's going to be the first name and last name. That's going to be assigned to it. And then we're going to do something with it. So here's another example where we've got a ship. So remember, so now we have ships3.java. And so if you run out to the examples folder and get that one, you can take a look at it. And in here, we've got the new addition of the public ship3. So although we have the keyword public, we still don't have a data type. There's no data type. There's no return type on this. What is it going to return to? It doesn't return to anything. So it's not void either, because void is a return type. So instead, there's just no return type on it. But instead, we have here public ship3, and we have an x, a y, a speed, a direction, and a name that's coming through. And then this dot x is equal to x, and this dot y is going to be equal to y. Now we're using this. You're wondering, well, how come this didn't have this in here? As I was mentioning before, it's legal, but in convention, by convention, if we put this in here, and we know we're talking about this ship. Because what ends up happening is inevitably we'll end up inheriting something from this. And then we know, well, each one of the thises in the line can set their own data, and they can use their own variables. So. And this is all review, so stop me if there is something you want any information on that, because I'm going through this at the speed of light because we're reviewing. So, void move, so that one does have a return type, and that's our method to move it, and we'll print location. So you're not going to necessarily put a line of code to print the location out in main. Instead, you're going to create a method to print the location inside of the object. It's a little bit more control. So inevitably, what's going to end up happening is here's now test number 3.java. See how much smaller it is? So the driver programs should be really small, and the objects themselves are going to be large because they're going to contain all the data members, member functions, all the functionalities enclosed inside of those objects. We write the objects once, we use them over and over again. How many times are we going to write test 3? A lot. So we will make that small and more efficient. That way we can use it, you know, to accomplish tasks with as less effort as needed to be more efficient. So here we make instances of objects inside of the main driver program. We have ship1 and ship2. And then we're going to ship1.move, ship2.move, print this, print that. Thing. So this is more typical, you know, 1, 2, 3, 4, 5, 6 lines of code or so. So don't really have to do very much in the main program. So, and if we run it, we get the same results. The program itself is really doing the same thing over and over again. We're just reorganizing the code as we go through. Major points are the format of the constructor definitions, the this reference, the destructors. There aren't any. So on the exam, I'm sure there's don't have it in front of me right now, but I guarantee it there's some sort of a question on constructors and deconstructors and copy constructors. And, you know, none of those exist. All you have are constructors in Java. So you won't get tripped up on the question, hopefully. And what does new do? The new operator actually explicitly calls the constructor. Yeah, it creates the object. So allocates the memory, creates the object. Do we have a delete in Java? No. Why would we have to have one? What would delete do? Nothing, essentially. Because we have automatic garbage collection in Java. So constructors are explicitly useful for supplying values of fields. Okay, so assigning the data members values, which is why they're used. So notice the constructor name must be exactly the same name as the class name, and there's no return type, not even void. So don't bother putting void in there either. So let's look at a little review of the this variable, which we covered also in one of the first 2 weekends, probably the first one actually. So the this object reference can be used inside of any non-static method, because there is no this in a static method. In our static data, there's no such thing as a this. This is the instance. So it's referred to the current object. The common use of this is references are, in this particular case, to pass a reference to the current object as a parameter to another method. And here's an example. Here's some method this. What are we passing? Ourselves. We're an instance method, or we're an instance object, so we're going to pass this to something. So that's actually common syntax, and we'll see that in an example coming up. To resolve name conflicts, that's where we used it for up here. We said this.x, this.y resolves the name conflict here of, what's going to be in here? Here we go. This resolves a name conflict. This gives us reference to ourselves. So some method this, run it on me, or send me to it. To resolve name conflicts is going to essentially resolve the fields. More so in inheritance, we use both actually, as I mentioned before. This would resolve, well, which object actually owns this field name? This one does. And so if we say this inside of it, then we're basically specifying our environment in variable scope. So note that this is the only necessary to say this.field name when you have a local variable and a class field with the same name. So if you have two, you have to, it is required actually, if you're using it with the same name, because you have to say this one for the instance versus the class. Otherwise, you can use the field name with no this in front of it, it works just fine. So only necessary when you have a local variable and a class field with the same name. What's a class field? Well, it's going to be something inside from a static level, also maybe something inside that from a local variable. Inside of a method, which is trippy because you can create a method, right? Yeah, this page left intentionally blank because there's no destructor. You can have a method that uses first name inside of the method, and then you have a first name, and the first name belongs to the class. And you can use the same first name. And you can say first name is equal to first name. We did this actually in a couple of examples. When we said set name, first name. First name comes in. First name is equal to first name. That's going to give you a compiler error. So it's required to go this dot first name is equal to first name if you're going to do that. Most people would avoid the error by simply just renaming it, calling it something else, not using the same name. So That would be considered a local variable conflict with a instance variable. All right, so the person class. Remember the person class we did? Going back down memory lane, the idea here is the goal is to make a class that represents a person's first name and last name. And we have 4 iterations of it here through the approach. So the person with instance variables only, and this is an example you can find. We're not going to go through the whole thing, but it's in the folder for persons. So you'll see if I open it up here, there's a person 2 test, person 1 test, person 1, person 2, person 3, person 4, same as the ships. So this is a great reference tool for you to kind of go back down memory lane and see how the class person object was put together. So the person with the instance variables, person with to get the full name method, add a constructor, then change the constructor to use this. It's essentially the concept. So here's first iteration here, just showing you the code without going through it because I don't need to. We already did this. We spent a good couple lectures on the person actually in the beginning. So person test, person P is equal to new person, P.Larry, and first name, last name, and then printing it out, not doing very much. And then in iteration number 2, we added methods to it. So we have a get full name and getters and setters. So not in the slide set, but just refresh your memory on that. They're accessors or modifiers, sometimes called accessor modifier, sometimes called setters and getters. Most people are calling them setters and getters these days because we're setting the information or we're getting the information. They come in sets. In fact, Eclipse has got a button for you. You just click it and it says, create my setters and getters, and we figured that out a couple weekends ago. So. And then the concept of the constructor even automates it even further. So it takes and creates a way of automatically initializing it instead of having to go, you know, first name, last name is equal to this, equals to that. So and then one line of code over here. And notice what's going on here. Person test.java is big, and this is small. And then we got kind of medium, medium. And by the time we get down to the final version, we're noticing small, bigger. So the class on the left is getting bigger, the class on the right is getting smaller as we perfect and we improve the design a little bit, which is kind of the phenomenon that exists. So, which means your driver programs are smaller than your classes. So if you've got this going on, the opposite of this going on, it means syntactically you're probably correct, but I don't know. Object-oriented wise, you've got some fundamental problems in your design because this is way too big for what this is doing. Does it really matter that it's big? No, but if you're going to follow good design practices, you're going to try to make the main program as small. Your classes are going to be very functional. So here's the addition of the constructor. Now we have the constructor working over here. And we could put something in here that says, you know, instead of printing it out in here, we could just put a print function in here. So here's another example. Using this with arrays. So this is the end of the constructor. So adding a constructor to this example. If I were to make this one a little bit more, I could put this over here and just say print, and then call a print method, and not have to put the code in here to print it. This actually, there's pros and cons to making a print method. Because what if you wanted? What if there's a date you wanted to print it in 4 different formats? How would you know which format you were going to print it in? So a lot of people would opt to put it into the main driver program because then they can basically customize the way the date is printed. Or you would have to create like 4 different methods or something. Print it with the year first, print it with the year second, print it with the year there, or whatever, you know, all these different options you might have. If you did that, then you'd have to remember, well, which print method do I need to run, kind of thing. So iterator 4 is, it's added this to it, and using arrays inside of it. So here we have the constructors with the this variable inside of it. So over here we have this added here. In the last iteration of this we didn't have this, and here we just had first name is equal to first name, I believe. Yeah, first name is equal to initial first name here. But if we change this one to first name instead of using initial first name, we're going to, without the this, we'd have first name is going to be equal to the first name. and the compiler is going to come back and complain for us because it doesn't know which one we're using. And then we have the introduction of the array. For remember the arrays, we can put objects of like type in an array. And then we had the is-a relationship, if you remember that, where we can take, as an example, if we had a person, and we're going to see that coming up in another slide, but a person, and then from a person we made an employee, and then from an employee we made a staff, and then we made a teacher. I believe we had a programming assignment of this nature as well, where we made an array of objects, and in the array of objects we stick all these people. Well, they're all people. So if you used, in this particular case, a person array, then you could cast through the is-a relationship all those other people, you know, the employees instances, the staff instances, and all those other ones, cast them back down to people, stick them all in the array, because we remember from traditional programming that arrays all have to have the same data type in them. You can't mix and match objects of different types unless you're playing around with the utility class and you're using something that's you know, a different type of an array. You know, but long story short, what you're going to want to do here is have an array of people. Well, just the same way as a regular old person, but we use those opening and closing brackets. It looks like a square in here, but there's really a space. It's two different symbols put together. And then we have a little loop in here that's going to go people.length, which is going to be a built-in method that we're going to do on the array, because we have built-in methods for arrays in Java that we don't. We actually have that in other languages as well, but it's a nice little way of getting the length. And then people I, you know, is going to be 0 through the length of 20, because we created this array with 20 elements in it. And then we have for person, colon, people, which means for each one of the people in there. It's a shorthand on a for loop to iterate through. So lucky for you, on the final it's multiple choice, so you don't actually have to write any syntax. But in this particular case, you probably will see a question on the is-a relationship. So you have a bunch of objects that all get stuck in the same array, and it'll be more like, you know, which one of these is the better syntax for it or something. So you might look at pieces of syntax, but you don't necessarily have to write any syntax, is what I'm saying. But you want to be familiar with how to create arrays of objects, and you want to be familiar with casting, because arrays are going to require that all the object types that are stored inside be of the same data type. So make sure that you cast them. And then we have the helper class for iteration 4. So what does that mean? Well, in this iteration 4 here, we added the constructor to this in the arrays. And then we have this helper class. What's a helper class? Well, here we have class name utils. And then we have another class here, we have a random last name method that we're going to run here that's static. What does a static mean? Well, we're going to run it from name utils dot random last name, just to generate a random last name for us. Smith plus some number is going to be returned from this. So if we run well, I don't know if it's probably not in here. It's not in here. If we run this here, you'll see it in the example. I think it's called name utils, actually. And it should be out here as well. If not, it's in the second set. No, here it is here. And there's another driver, test 4, I believe, or test 5, that will run this in here as well. So I believe it is, where are my tests here? Test 3. I believe it's probably in test 3. No, person 4 test. This is the one that I'm looking at. Let's take a look here. Here it is, name utils, that random first name. So test number 4 is giving you an example of using a class static method, and the static method that we're using is random first name, and it's from the class name utils. So it's a utility method. We're not making an instance of it, we're just using it. So a lot of people would actually prefer not to have to make instances of things if you're gonna, it's like the math. So you never make an instance of a math object, you just go math dot something and you use it the same way. Well, you can do it yourself, and this is how a way of doing it yourself. You're creating the class name utils, you're putting in a file name utils.java. You're running in there and you've got a piece of public static data that you're using, and you're running a math, and actually, which is kind of funny, is inside you're running math. So you're running a static inside of a static, actually. Math.random, and you're going to return John plus something, and then you got first name and last name got random, that you're going to essentially create a random first name and last name, starting out with John and Smith. So don't worry about the implementation of that. Just know that you can run a static method like that. And if you're going to run a static method, you're going to run it statically from the class name. Later iterations, you can use an accessor method, setters and getters, which I'm going to demonstrate next. And then you can document the code using JavaDocs. We talked about JavaDocs briefly towards the end of the second interactive meeting that we had, the intermediate session we had a couple weeks ago, if you remember. Didn't look at it, but I've got another example to show you today. Or we might look at it tomorrow. It's kind of like one of those things, we looked at it in the Android class. It's kind of like one of those things that, yeah, it comes in handy. Is it worth the documentation efforts? If you documented it internally using the JavaDocs style, you press a button, it creates JavaDocs for you. And those JavaDocs can be uploaded to a website or can be used in your documentation. So it's kind of a way of automatically creating your documentations. We can do this with testing as well, using JUnit. Built into Eclipse as well. We can automatically, sort of automatically create test cases. So you still have to write, just the same way as you have to write JavaDocs, you still have to fill in the body of the test cases as well. So. And we're going to see inheritance coming up in the next slide set. So to review that concept as well, making an employee based on a person, which is what we did in the first weekend. So anything in here? Nope. Because I'm using this as a review component, I'm kind of going through it on the fast side as I mentioned before. So don't necessarily need to read through all of it. However, if you'd like, you can download it. So this is Basics 2. And for those people who came in super late, because I still see people coming in right now, these tutorials that I'm going over, along with the source code examples, are in the programming tutorials section. So, all right, moving right along, I'm going to go through the second part, then we'll take our first break. Those people who are, because some people are just showing up, which is kind of odd. But so this is called Basics 2. And again, there's another complementary source code file that goes along with it called OOP-more that goes along with Basics 2 if you unzip the file. This is what I'm going over now. And in here we're going to see the employee class. So it's a review of the employee that was created from the person. Same thing we did the first weekend, actually. And this is also your opportunity to ask questions because I'm going to assume all this stuff is review. So we're going to talk about the concept of abstract classes, interfaces, the use of the @ directive, the @ override, the @ depreciated, and @ directive, the class path, packages, visibility for other than public and private, and then JavaDoc details. So I'm not going to focus too much on JavaDocs. There are no questions on the final exam related to JavaDocs, so you don't have to worry about that. Abstract classes, though. That concept is important. There's somebody talking in the back, and I can't, it's kind of irritating. So if you're going to talk, take your conversations outside, please. So let's see. The idea of abstract classes. So as I mentioned before, and I'm kind of also reviewing good design techniques as well this morning, you want to keep the main small. Well, you want to keep your classes small too. And say, how do you keep your classes small? You don't want to have to reinvent the wheel. Instead, you want to reuse the design and build a solid foundation. How do you know what the design is going to be until you get later on? So abstract classes allow you to create the concept without implementing the concept. So by making it abstract, what you're doing is essentially making it expandable and adaptable through the inheritance. A classic example of this is with the shape and the rectangles and the triangles and stuff. So if I have a base class and I call it shape, it's probably going to be an abstract class because inside of that class, if I have a method called area, how am I going to come up with the area of a shape? I can't. So if I delay everything, an abstract is just another way of delaying implementations until you're actually going to use it. If I define what a shape is, and I define what an area is, and I implement the area, and then I inherit another class from it, and then I run the area without overloading that method, I'm going to get a really weird area, because the area of a different shape is going to be different. So long story short, if I don't want that to happen, I don't want the risk of that to happen, I delay it. There's no law that says I have to make it abstract. There's no law that says I even have to put an area method in there. But if I'm going to, design-wise, it's much better to make it abstract until I'm actually going to implement it. So that's the overall idea. So a class that you cannot directly instantiate either. So you can never make an instance of an abstract class. You can't do that in any language. Why? Because it doesn't exist. It's a concept. It's a class, but it's not meant to have an instance. But when you make an instance of the object, you get it. So if I made person abstract and then I made an employee on top of it, we actually did this. We can make an employee and use them as a person because the object is still in there. Remember, we used the is-a relationship to upcast a employee back to a person. And then, but if we said person P1 is equal to new person, but person is abstract, can't do it. But if we made an employee and then we used him as a person, that works. So the instance is there, we just can't make an instance of a person without making an employee. Because we need the employee to define the person's attributes and the person's methods. So you can subclass it and instantiate the subclasses, which is what that means. So on the exam you're going to get classes, subclasses, super this, all of this stuff here. That's what it means when you subclass. You're making a class from another class. How do we do that? We use the keyword extends. So we're reviewing inheritance here as well, which is different than implements. So in Java we have a single line. We have a single line inheritance. One class extends another class, which extends another class, which extends another class. That is not multiple line inheritance. That's single line inheritance. We achieve multiple line inheritance through using inheritance, but also interfacing. So we have multiple interfaces that are able to be used with one class. So one class A extends class B, implements D, E, F, G, H, I, J, K as much as it wants to. When it implements an interface, I'm going to review interfaces as well since I get past abstraction here. That gives us a couple of different things. It gives us the protocol kind of concept, which means it gives us a contract. It gives us an is-a relationship, or a way of invisibly tagging the class. It gives us multiple inheritance. It gives us a lot, actually. And it's more true to object orientation than it is when implemented in languages that don't use an interface. Going back to C++, no interface. There's no such thing. There is multiple inheritance, however, which is used like an interface. And the interface concept is there. There is a such thing. I don't mean to say that. There's a such thing, but you never implement it. You don't use it the same way. So instead, if we're writing this example in C++, I could say class A is inherited from A, B, C, D, E, F, G, all these classes, which gives us multiple line inheritance. So we still have multiple line inheritance in both languages. It's just performed differently because we have single line extensions with multiple interfaces. In Java, we have multiple extensions in other languages. So just keep that in mind. That's what makes Java a bit unique. Also makes it more true to object orientation. So when I say true to object orientation, I mean some languages have a weak interpretation of object orientation. Some languages have a strong one. Java's strong. C++ is very weak in terms of its implementation. And other languages that are more Java-like, like C# is stronger in terms of its object-oriented implementation. So let's take a look at the syntax here. As well, we have the keyword abstract, which we don't get in C++ actually, and we don't get in other languages. We get that, yeah, it's Java. Java is one of the best object-oriented teaching languages because it really does have everything in it, and it's more true to form. So we actually have the keyword abstract that's used. So if you see that used in a class, it means you can't make an instance of that class, and it means that that class is not. It could be You can have everything in it implemented and just have one method that's not implemented, and the entire class is now abstract. But half of it or majority of it is implemented. So you can take an implemented class, add an abstract method to it, make the whole class abstract. Still can't make an instance out of it. But if you made an instance out of a class that used it, that implemented it, then you can go back and use all that original functionality as well. So it's kind of interesting how that works. All right, so public abstract, some type of method in there with no method body. So that's where we're getting our method prototypes. So in some languages we have a .h and a .m or .h and a .c++. And here we have abstract class or non-abstract class, which is essentially the same concept. So then we have another one here that's not abstract that might be implemented. So the motivation here guarantees that all subclasses will have certain methods. So let's make a collection of mixed types, essentially. So we're going to make a collection here of different types of classes that work together. Here's an abstract concept here, and it goes going into the shape that I just talked about. So and this is the same example we used in the first or second. I think we had seen abstract classes maybe in the second weekend. So we have a circle and a rectangle class. Each of them has a get area method. They're going to be different. So the goal here is to get sum of areas of an array of circles and rectangles. So why does this fail here? Object, we've made an array of objects here. We call them shapes. It's going to be equal to new circle, comma, new rectangle. Interesting. Double zero for object shape. Shape sum is equal to sum plus shape get area. Problem with that is we're using them together as objects, and we don't have, well, object data type does not have an area method in it to begin with. So we can't use that. This is going to fail for many different reasons. But first of all, how are we going to get the area of a circle and an area of a rectangle from an area of an object? An object is abstract, actually. Excuse me, object is not abstract in Java, which is funny. You can actually use object. But theoretically, it is abstract because it doesn't implement anything, but it's not an abstract object. So we can do this legally. In fact, we can take everything and reduce it down to an object. We can create an instance of an object, and we can create, we can cast other objects through the is-a relationship back to an object. That's how we create polymorphism in the language. We create a generic object. So as I'm going through object orientation here, let me review a few concepts. If you remember, on weekend number 1, I described object orientation as a pie. And this is a repeat of all the object orientation stuff for the review as well. There are a couple questions on the final regarding a pie. And it's not what is a pie, it's the concept that's associated with it. So if we remember, a pie is the acronym, or the mnemonic, I think it's called actually. A stands for abstraction. Yeah. There. Oh, you got it. See that? You walked away with something at least from the previous couple of classes. So A is for abstraction, or A is for apple, no, for abstraction. And abstraction, examples of abstraction in the language is the object concept. Well, that's how we're also getting abstract classes. It's abstraction. It's another form, which is why I'm bringing this up right now. So abstract classes provide us with abstract objects. Anything abstract is not implemented. So how do we know that our abstract classes, if all objects are abstract, if all classes are abstract, in concept for object orientation, we can make instances of it. It's different from an abstract class. As an example, the object of the person, or the shape, or the rectangle, or sort of just take any object out there. It's abstract. It's an abstraction of a real world object that's represented in a programming language, in a programming environment. But person doesn't actually take meaning until we make an instance of it and we use that abstraction to create person A, person B, person C. So the language concept is built around the abstraction of the generic object that turns into a real object when we start using it, when we make instances of it. So that's a form of how abstraction works in object orientation. The P is for polymorphic behavior, and that's expressed through the is-a relation. Well, one form of it is through the is-a relationship. And the is-a relationship tells us that the person can turn into an employee, can turn into a manager, can turn into a staff. But what are they really? They're a person. So with that is-a relationship, when you make a CEO, you get everybody all the way down to the person. And so you can take and transform that, which is polymorphic. It's like when you're at work and then you're at home. You know, well, most people define themselves by what they do for a living, but that's really wrong because that's a different class entirely. But long story short, you have that is a relationship with yourself in your human life, actually, and you're polymorphic. You turn into a soccer player, and then you turn into a football player, or you turn into a, if you're an athlete or whatever, you turn into a student. But when you're not a student, when you're at work, you're something else. So, and I'm a student, actually. I take classes, and I'm not a teacher in those classes, So that's polymorphic behavior. Also the ability, so that's one example of polymorphism in the language. Another example of because the exam's going to have, examples of polymorphism in the language include, so don't limit yourself to just that. Another one, the ability of the object itself to adapt. How do we create polymorphic objects? Well, we create multiple constructors in the language. So we can create a person with a first name and a last name. We can create a person with no name at all. We can print out the person's first name, last name. We can just print out the person's first name. We can just print out the last name. It's kind of a simple example. There's not very much to print out. But go back to a date. We can print out the date in this format, the date in that format, the date. It's polymorphic behavior. Also the ability to take on different types and numbers of parameters in methods. We have polymorphic methods. So we can say print a float, print a double, print an integer, which allows us to adapt to different data types as well. And then we have the concept of inheritance, which is what I'm leading into now. And the inheritance component of it takes an object and turns it into another object. It's like evolution. So Darwin's theory of evolution, we're all apes, I guess, monkeys, but we don't look like monkeys. Well, some of us do, but I'm just kidding. Not all of us. Well, okay, so we adapted into humans. We lost our tails. I don't know if we lost any fingers or anything. I think we're supposed to be losing toes soon, but we'll see what happens in another 200 or 300 years from now. But long story short, we've inherited and adapted survival of the fittest. Some genes have gone away. Some things have been introduced. So do the objects in the real world. So do the objects in programming languages. We take a person and we turn them into the CEO through different levels of the hierarchical inheritance that person transforms into. Just like the shape turns into a circle, turns into a rectangle. And then the interface part of that gives us our adaptation. So think of, so interfacing and extending is all part of inheritance, because the interfacing gives us the adaptation to provide the inheritance. So you guys are sitting in here learning Java, you're interfacing. You're obtaining an interface. So later on, hopefully what you'll do is use the interface, maybe get a job, Java programming, or maybe get into Android development. So you'll use the interface, you'll implement the interface to apply it towards a skill. So you come from a person and then you turn into a computer science major, then you turn into a Java programmer or Java executive or Android developer or something that uses that skill, which is the concept of getting an education normally, is to give yourself new interfaces because you're going to implement it. But let's say, for example, an athlete has different interfaces that they've implemented. Students have different interfaces depending upon your major. I mean, unless you're studying medicine, you're not taking any medicine classes. You're taking computer science classes or something like that. So you're evolving and inheriting in a different type of object than a medical student or a law student or computer science or software engineering student. So the finished product at the end is different, theoretically. Sometimes the finished product doesn't match what you want to do, though, so that's a totally different class in itself. That's the philosophy of the student. But long story short, that's the I in Pi. And then we have encapsulation. Encapsulation takes all of that stuff and hides it. So encapsulation works against our visibility. It takes and hides the interface. It creates the public interface, hides all the private stuff. Encapsulates concepts. Once we create the concept of a shape, and we have a concept of a circle and a concept of a square, we don't worry about implementing that anymore. We just use it. So a lot of people think, they want to add a reuse. They want to put, if you say, well, what are the components of object orientation? Usually they add in information hiding, or they add reuse in terms of it. But encapsulation gives us both. It gives us reusable items, and then it gives us information hiding. Because once we create the concept, we just reuse the concept. Actually, let me pause this for a second. Okay, we're back, and we're going to finish this lecture, yes?
So, what is the difference between an interface and an abstract class?
Let me talk about interfaces and abstract classes, because I have to get us back on track anyway after this mini little break here. An interface is like a protocol. It's a set of rules. It is not a full implementation of a class. In fact, it has the keyword interface instead of abstract, which is one of the interesting things about Java is each one of the components is labeled appropriately. So instead of everything just being a class, we have abstract class, interface, XYZ, or whatever we're going to call it. And when we implement the interface, we include the method implementations for the abstract classes. So in some cases, abstract classes and interfaces are practically identical. And an interface is just like an abstract class, but we call it an interface because, well, that's a good question. Why use an interface instead of an abstract class in that case? Well, we use it for different reasons. It's essentially the same thing, but we're using it for different purposes. The abstract class, we're delaying it because we put an abstract method in there. It's really a fuller class. So we create this abstract class. We start out making a regular old class. We end up putting, if we put one abstract method inside of that, the whole class turns into an abstract class. And if we're going to do that, then we're going to probably have more implemented in there. So we have the concept of the shape implemented with all the dimensions and stuff, and then we have this little abstract area method in there. And in that particular case, because we have that abstract method, we have the abstract class. When we use it, we're going to use it as we're going to extend it essentially in terms of inheritance, and we're going to inherit from it. It becomes part of the object itself, and is a relationship where we can take a rectangle and go back to a shape. Compare that with an interface. Interface doesn't have anything in it. Interface doesn't have any partial implementation of anything. It is just a contract. So what do I mean by contract? It's a bunch of method prototypes that says everybody who abides by this interface is a member of this and has implemented these particular methods, and we don't have an is a relationship with it. So we don't have an object instance or an object because it's not part of the inheritance. It's not really a class. It's an interface. So we can't take all of these objects and turn them into the interface. It doesn't work that way. If it was an abstract class like shape, we could take them all and make them all shapes. But if we have all these shapes and we have a printing interface that we're using with them, then they all have the same method. So it's like we're almost like stamping them all with the same label as well. We're saying, you implement the interface print or printing, and you implement the interface printing, and you do it, you do it, you do it. If you all implement this interface, it means you all have the same method. So when we run that method, we know the method exists, which gives us our contract or kind of our protocol. Some languages like Objective-C call it a protocol or categories. It's a protocol where they say you're going to implement this. It's a bunch of protocols, another word for rule. It says if you're if this class is abiding by these rules, it has this method, it has that method, it's able to do this, it's able to do that, and then we can put them all in the same grouping by their protocols or their interface. It's also used for tagging. Interfaces are used for tagging a lot as well. What I mean by tagging, I could tag this as a shape, which means I have a variable in there that says, my type, and it equals shape. And I put that in the interface, and all of the instances of all these objects that are implementing, abiding by the interface, have this tag inside of it. And so I can, say, are you a shape? Are you a shape? Are you a shape? So I can ask the object what it is. If it has the tag in there, it comes back and says, yeah, my name is shape. So then, it's all abiding by the same grouping. So if you think of abstract classes as a way of delaying the implementation of behavior, and think of interfaces as more of a contract, more of you're a shape, so you're supposed to have all of this stuff. And you can do the same thing that you can do with an interface with an abstract class, which is kind of weird. I mean, going back to that shape and the concept of the area, you could put an area method in an interface. You could put an area method in an abstract class, and you can use them both together. So that's where all the confusion comes into place. And people, well, how come we're not going to use that? Well, a lot of people take an abstract class and turn it into an interface because we don't have multiple inheritance. So you can only inherit one class from one class. So if I have a shape and I'm going to make a rectangle that extends shape, and I can't go shape, comma, another abstract class, but if I take the abstract class, turn it into an interface instead, then I can extend this class, but then I can implement this one. Multiple interfaces, only one extends. So I can extend it. Why they made it that way is beyond me, But that's really, in a nutshell. There's you can read a couple chapters on it, but in a nutshell, that's the difference. It's really the same, but it's used in different ways for different reasons, for different objectives. And syntactically, you actually call it an interface, so you put the word in. It's in a .java file, but there's an interface in there. So instead of saying public class such as public interface something, it's the same way you say abstract class. You actually write the keywords in there, which is different and more true form to object orientation than some other object-oriented languages as well. So hopefully I answered your question. Okay.
And all the
Yes?
methods in an interface are
Required to be implemented. Or
and
you
they are abstract, right?
and they're not abstract.
In interface.
They're not abstract. The interface has, but in concept they're abstract, but they don't have to be defined as abstract, because what you're doing is you're putting in a bunch of an interface in Java is equivalent to a .h file in C++. If you're not familiar with C++, then a .h file in Objective-C, or a .h file, it's called an interface file. An interface file contains a bunch of method prototypes. No implementations, just the prototype. What does that mean? It's the definition of the methods. So you take the .h, aka interface file, you implement it in a Java file, and you're writing the method bodies. If you leave out one of those methods in there, then you'll get an error. So that's where the protocol concept comes in, because it's enforcing those rules, which means if I have this method in the interface and I'm using the interface, I have to put the method in my class implementation. Do I really have to fill it in? No, but I have to keep the empty method body in there. So you see a lot of interfaces that are implemented with blank methods, or not blank, but empty methods, like it says, public void, print me, but print me is empty. And because if you don't put the prototype in there again, or the method implementation, but leave it blank, you get an error message from the compiler, because it says, you're interfacing this interface, you must implement these methods. And then you usually get a prompt, would you like to do it now? Okay. And it populates it out with a bunch of blank methods. And then when it does that, if you use the auto tools in Eclipse to do that, you usually get an @ symbol, @ directive, which is a comment, and it'll say, implemented interface, or interface something, which is basically telling you, oh, this is in here because the interface has it in here, which means you have to implement it, which is the same concept as an interface in other languages, but Java doesn't have it separated out like that. So that's kind of an interesting trivia kind of thing, actually. But those are good questions. Any more?
Yeah, one more.
Okay, I'll take it for 2 points.
If we are implementing an interface, and suppose if we end up implementing the methods of interface, so do we need to define the class as an abstract?
No. When you
If we have like 3 methods in an interface and we are providing body we are implementing just two and not the third one?
You have to implement it all. That's the contract with an interface, and what makes an interface different from an abstract. Abstract, you could just keep it abstract again, keep it abstract again, keep it abstract again. And if you're going to have one abstract method, the whole class has got to be abstract. So you can have an abstract method extend another, abstract class extend another abstract class, extend another abstract class. Eventually, it's going to turn into a class. The interface, even if it's empty, you got to stick it in there. If you don't implement the interface, you're not abiding by the rules, and you can't use it. It's required that you implement, can be blank, but it's required that you include the method bodies for all of those implemented methods in the interface. If you don't do it, the class won't compile. But really, you're leaving it abstract if you leave it empty. It's not going to do anything. It's just going to be empty. Most people would put like a little system out in there and say, hey, not implemented yet. So if you got that printed, when you ran the print on a circle, and it's, hey, not implemented yet. Oh, forgot. Go back in there and implement it, I think. So. Very good questions. Anything else? No? Okay, good. We'll go over the assignments after when we take our next break, actually. I just want to finish this lecture. I got 10 slides left here. All right, so now going back down memory lane. Why does this fail? Well, this is going to fail for many reasons. But here's our solution. We make shape abstract. So we have public, and this is the way the class is defined. And if you go into shape.java, which is going to be in our second grouping of examples. Do we have shape in here? No, we have employee. Well, we don't have shape in here, but we have speed boats and boat tests is what we're going to end up doing here. But this would be in a class called shape.java and a file called shape.java. Although it does have the keyword abstract in here, we have abstract class shape. It is the same file name. And in here we have this method printInfo, and printInfo is going to print out the shape, and it's going to get the simple shape name. And then we have circle, and similar for the rectangle, we have a class circle that is going to extend shape. And so we extend it just like, the only difference between this class and any other class is the word abstract in there. It's implemented and used the same way. So here we extend, so public class circle extends shape, and we have a method getArea inside of that. And this is the getArea method here, and this is why the class is abstract, because we have an abstract method. So we use a keyword abstract. It tells you that the methods hasn't been implemented yet. And notice this is a method prototype. It has a semicolon at the end of it. Doesn't look like a regular method implementation. Interfaces. So I talked a little bit ahead, but here we have the main idea of the interface. More or less an abstract class, but without any concrete methods. You can't put any methods in it. So if you have an interface, and you got concrete methods in there that aren't abstract, that are just implemented, it's not an interface anymore. Interface is strictly an interface. Nothing's implemented in it. It's a bunch of blank method bodies. So the syntax for it, you use the keyword interface. So public interface, some interface. And so if we put this in here, oh, I can't highlight the word. If we put this in here, I was trying to highlight the word. Then we've created an interface. It still goes into a file called someinterface.java, because everything goes into a .java file, which is different than some other languages that have .h's and .c++'s and stuff. So usually they call it a .h. And then for a header file, from the old includes, remembering we have imports now, not includes, but it doesn't really matter. It's the same concept. You're including it in terms of the implementation. So we have here public class, some class that implements, and so we use the keyword here implements instead of extends. So this one up here uses the keyword extends. See, this one I can highlight. Extends means that we're inheriting. This means we're going to use the see, it can't highlight. Uses the implements the interface. So, motivation, like abstract classes, guarantees the classes have certain methods, but classes can implement multiple interfaces. So, I guarantee it, there will be a question or two with the differences between abstract classes and interfaces. And it's just, if you know the concept, you got it down, you can answer those questions no problem. So, you want to know what the differences are in terms not of comparing and contrasting, but in if you know what an interface is and you know what an abstract class is, than if I said abstract. You can inherit from multiple abstract classes. True or false? Can you inherit from multiple abstract classes? False. The answer to that would be false. You can inherit from one class, but you can implement multiple interfaces. True or false? True. So, I mean, that's the concept. And, you know, abstract classes don't contain any abstract. No, that's a bad question. Don't contain any abstract method. Why would it be abstract then? If you have one abstract method, the whole entire class has to be abstract. True. Can you put a partially implemented method in an interface? No. False. So an interface can contain an abstract class. An interface cannot contain an abstract class. If it does, it has to be an abstract class. You can't put abstract classes inside of an interface. But every single method, abstract methods inside of an interface. Every single method is abstract inside of an interface, but you don't use the keyword abstract in there because they're not methods. They're method prototypes. You don't put methods inside. Methods don't belong inside of an interface because you have prototypes, which are the method definitions or declarations, but they're not the implementations. You can't implement anything inside of an interface because it's not a class of any sort. Classes have three components: identity, state, behavior. Interfaces don't have those three components. They don't have identity. They have identity. They don't have states, and they don't have behaviors. Identity is the name of the object, so a person. And so technically an interface doesn't really actually have an identity either. It's a protocol, so it's a rule. So it says printing on it, or it says floating, or saleable, or human. We could have a human interface. Human computer interface, no, that's a joke. We can have a human interface to a person. Nobody have people that aren't humans though? I don't know. So I don't know if I'd make human an interface, but we can tag with it. We can tag with interfaces. We can have methods, but they're not instance methods. They're just tags. What do I mean by tag? We can set a variable, you know, like string identity equals human. And then we can go into the Matrix or to the, you know, one of these futuristic shows and go, what are you? And scan you. Oh, look at, there's your tag. You're a human. You know, and that would be part of the interface that we attached to the object, made it human, because we tag. That's what I mean by a tag, by the way. It's a piece of information that's encapsulated inside of the object. It's not used in the object for anything. I mean, do you use your, well, maybe people are humanistic, but abstractly, do you use like your tags of your name to identify? It's your identity. As an object, you have a name, you have a social security number. That's why they call it identity theft. It's an identity. So objects have identity. That's usually the name of the object or something. We can attach an identity through an interface sometimes by tagging it, but we're not using it like an object name. It's not. Our interface doesn't define who we are, because just sort of human doesn't make us any different. We're all human. It's not going to define who we are. It's not going to give us anything that's going to say, you know, that we have any ability. So, I mean, some humans are in prison, some humans are free, some humans, you know, we're all just different humans. So, interface is the problem, some of the areas. So, you're going to want to get the sum of the areas of mixtures of circles and rectangles. But this time, you do not need shape class to have a concrete print info method. So if I were going to get the sum of the areas of everything, I'd put it inside of an abstract class. If I wanted a print method, then I'd use an interface for it. Why interface instead of an abstract class? Classes can directly extend only one class. So one class goes with one class, abstract or otherwise. Classes can implement many interfaces. So if it's generic behavior, stick it in an interface. Why? Because multiple classes can use the same interface. So interfaces are sometimes used to create groups of objects as well. So all of these objects are shapes. So if I have a shape interface, then I can define, well, what does a shape have? Shape has an area, It has a print. It has a get, set, and it has all of this stuff in it, right? So if it's a shape, then like I can say, what's the area of a circle? What's the area of a rectangle? What's the area of a pyramid or whatever? And I go, hey, this is something that I would think of. Or humans. What do humans do? Well, humans have names and stuff. So if I were going to create a human, I'd do an interface for that. I could do an interface for a shape. Why do we have to make it abstract? We don't. It's really just a contract. All shapes meet a certain characteristic. So, but we're not necessarily, we don't need to use it in inheritance. We can use it in interfacing, actually. So shape is actually kind of an interesting example because it can be both an implementation of an interface and it can also be an abstract class in concept. So here's another solution for this. If we were looking at the scenario here, the sum of the areas, well, why put it in a class, concrete class, when you don't need it? It's going to be a mixture. It's going to be different for different objects. So, but we want the concept of there being an area. So here we have public interface shape, and then in type of here, notice we're not making this abstract anymore. We have public double get area. And so we have one method here. We can have multiple methods, as many methods as we want, but as making sure that they're just prototypes of these methods. And then we have a circle. So we have the class circle that implements shape, and then we have a rectangle that implements shape. So whenever you see the keyword implements, you know you're implementing an interface. When you extend, you know you're inheriting one class from another. Cannot extend an interface. If shape is an interface, you can't say circle extends shape. You're going to get a compiler error. It's going to come back and say, hey, shape's not an object. And shape isn't an object. Shape's an interface in this example. Because we don't have an is-a relationship with that either. We can't, so that's why we call it tagging instead of is-a relationship, because an is-a relationship happens through inheritance and inheritance only. So a car is not a boat or a human. There's not going to be an is-a relationship with that. But if we have a BMW car, it could be a vehicle. So in terms of the inheritance, or if we have a grad student or an undergrad student, could be a human. Yeah, hopefully. Of course, some of you guys may not be humans, and I wouldn't know unless I scanned you for your interface. I don't know. Sometimes I don't think I'm human, so I have to scan and go, zzz, oh, human. Okay, good. Actually, I usually I feel human when I get something stuck in my throat and I can't talk. And my eyes water because I'm like dying here. Then I go, oh, I'm human. At override. So we have the at override going back into this. This is called an at directive, actually. So use the same way in Objective-C, the languages. What does that do? It's a comment. So we see this put in by Eclipse all the time. Just to reiterate and review the point. In the parent class here, parent class Eclipse implements shape. So we know that shape is an interface. And we have a child class. Here's a mistake. We have class circle extends Eclipse. Well, the code will compile, but when you call get area at runtime, if you read the small little notes on the side here, you're going to get a version from Eclipse. Since there was a typo in this name, it's a lowercase here, get area. It's actually going to work because we've created a new one. We've redefined it. So it's kind of a tricky mistake because this one here is a capital, this one here is a lowercase. We haven't overridden it. So what ends up happening is, and this is why, this is basically just giving a demonstration of the at directive for the override. Catch the mistake at compile time. If you really thought you were overriding it, and you put this at override in there, compiler's going to say, hey, no, you're not. This is a brand new method. You're not overriding anything. So it means you're implementing it. What does that mean? To implement an interface, you're overriding the methods. So we can override and we can overload. To override a method, we replace it. Which, I don't know, I like to use the word overwrite, when I write over something. But this is called override, which means we take the old one out, we put the new one in, we override it. It's kind of like going on autopilot, taking it off. So when we overload, we don't overwrite it. We don't replace it. We leave it alone. We just add another one to it. So technically what we did here was we overloaded. Now we have two. We have get area and get area. One's capital, one's smaller. Not such a good idea because then it gets confusing. Normally what you would do in this case is put something in here, get area A. So people overload methods by changing the parameter footprint. The parameter footprint is the number and the order and the information that's associated with the method. You're implementing a different method, has the same name, but there's something else. The return type can be different. The method list can be different. It can be the same items, just in a different order, and you've overloaded it. So keep in mind we have overriding, overloading. This override at directive is going to tell us we meant to overwrite it. We're going to get a compiler error that's going to fix that problem. We have this class path. Don't worry about the class path. We set it automatically in the environment variables. We did this on the first weekend of Java when we installed Java. Class path defines a list of directories for which to look for in classes. So what does that give us? Well, where all of our class packages and where all of our jars are located. So you might see a question on the class path on the final. And what does it do? It sets the location for the packages by definition. It's not going to ask you, what does it do? It's just going to be like in a sentence used in some description, probably package related. So what does that mean? Well, if you're not running everything all from the same directory, you have to set a class path to say that, hey, this utility, this jar file is located over here, and I'm using this one for my libraries, and I'm using this one over here. Because what ends up happening is you get these messages that come back and say, hey, can't find this class. Class doesn't exist, or not in the environment, or something missing. Because either you're not running it all from the same directory, or you don't have a class path set. You figured that out, hopefully, when you figured out how to run the compiler in the beginning. If you're using Eclipse, Eclipse will set it for you automatically. It's in the project properties. So Eclipse knows where Java is. It gets set for you, but no, there's a property in there that sets this thing called a class path. Because we know that when we create Java files, in fact, all of the programs we've been looking at today, if you look in the directory, it's kind of apparent here. You have .class, 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 .class. There's like 5 or 6 different .class files. And all those files work together, right, for one program. That's the class path. You said the class path. In this particular case, I'd set it to this directory, OOP-more, if I wanted to. Or you put them all in the same directory and you don't have to worry about a class path. You just change to that directory and then it can find all the files. Because Java is dynamically loaded, it needs to know the path directory. So another explanation for class path is that Java is dynamically allocated, dynamically loaded language. So when you load up main.class or myprogram.class, it's going to look for person.class and shape.class and all of the other ones. And it's going to find them and load them up into memory and only load one of each, which is the best part about Java. So let's compare Java with another language like C++ as an example. C++ being statically allocated, statically loaded, statically bound, statically everything. Every one of our executable files we get, the .exe file or the .o file, whatever it is on whatever platform we're running, has a copy of everything inside of it. All the objects are linked together and the copy is actually kind of big. And when you load it up, you get a different person, a different shape, a different version, and it all gets loaded up into memory. Not too time efficient, memory efficient. Not too execution time loading either efficient, because sure, it loads up faster because you just take a brand new copy of everything and stick it up into memory. It's quick, but it uses a lot more memory. So then they fix that problem by creating what's called dynamically linked libraries, DLLs. So you load that DLL file up once, or a shared object, a .so file in Linux. You load it up, it's in there, and then you link to it, which is called dynamically linked, which means your executable code is linking to a library that's already loaded up into memory. That's what Java does, but it does it for you automatically, so all of your programs are dynamically linked, which makes Java cross-platform compatible, but also distributed. So I have distributed objects in Java EE, if you take that course later on, if you haven't taken it already. But you load up one computer that has a bunch of objects that are associated with the functionality of that services that are running on that computer. You have another computer over here that has a bunch of other objects in there, and another computer over here on distributed systems, and you link them all together by the running program. The running program says, hey, this one's over here, that one's over here, and you can set class path to say, over here on this computer is all the accounting stuff, and over here is all the HR stuff, and over here is all the programming stuff. And your class path is setting the environment variable for those 3 different platforms and those 3 different computers. It's networked together, and as long as you have a network connection, it can go out, find it, dynamically link it. So the program can run distributed on a bunch of different computers. And you don't have to keep loading it up on every computer that you want to run something on. Makes it a lot more efficient. Does it take longer to load? Yeah. If it's not there, it's going to go find and load it. So Java, when you start it up, takes longer because you got to load the JVM if it's not loaded, and the JVM's got to load all the little objects out there and get everything set up so you can run Hello World, which is slower than if you just click on an executable file in Windows and it just loads up brand new everything. So one's more memory intense, the other one's not. Java is a very small footprint. The files are very small. C++ extremely high. Big files, huge files. Huge memory actually being used for that. You need a lot more memory on that. Because, you know, another piece of trivia, Java was an operating system for embedded systems originally. It's a printer operating system. It's a phone operating system. It runs on very small hardware with a very low amount of memory. Very efficient. It does run slower though. You make an entire operating system out of Java and you load it up on a computer. Like, well, Chrome's is a version of it, but it's optimized for desktop computing. It does run a little slower if you're going to do something outside of web browsing on it. It's going to run slower for word processing and for other things because it's using the memory more efficiently. So there's a lot more overhead in terms of that JVM and stuff. But anyway, I can go on for days comparing Java with other languages, but let me stop at this point. It does get into the concept of class path. So that was an explanation for in a distributed environment. That's going to connect all those computers together. We also have other settings for the environment. So if we're using Java EE Enterprise Edition, we're going to have different parameters, very similar to a class path, but it's going to set the environment for all the servers and more configuration. The difference between that and regular old Java is the configuration that you're doing. So putting in an RMI manager, putting in servlets, and creating a servlet environment, all different components to help orchestrate the networking part of it, more so than basic core Java. So, a package and packages organizes classes into groups. If we do that, then we can logically organize them on different computers and settings. So we put the code inside of the package, and then we add the packages, as we've seen before. So we make a folder called some package in Eclipse, and then we put the stuff in there. Motivation for this? You only have to worry about the name conflicts within your package. So if you're familiar with C or C++, you've got that using namespace. There's no such thing as a namespace. Well, there is. It's a package. Namespaces are packages in Java. Packages give us environment settings. So if we're in this package and we have Hello World, we're going to use this one. If we have another package that has Hello World, then we switch to the other package and we use Hello World over there. We can have multiple Hello Worlds. It's like directory structures. You can have multiple files, multiple names, and everything. You want to include multiple? You include multiple packages. So we import the packages at the beginning. We're not actually importing anything. It's not like an include. So the differences between the import and the include is used to link actual files. So in C++, we include iostream.h, string.h. We're linking the object code for those interface files into the executable code. In Java, we import. I mean, bring all that stuff in here, bring it into the environment so we have access to it just in case we want to use it. We're not including anything. So you can put in a ton of imports. Doesn't affect what's being linked. Actually doesn't affect it in C++ either, because if it's not in there, it's not going to link it. If you're not using it, it's not going to link it. But long story short, the word is called import instead of include because we're importing the environment into our package space. So it's for a package in terms of the concept. Just to refresh your memory on those visibility modifiers, because we are reviewing today, public is accessible from everywhere, as I mentioned before. I don't really have to go into this because I've been talking about it all morning so far. But accessible anywhere an instance of the class is accessible. So that would be the public. This applies also towards package and also everything else. So classes, methods, data, packages, everything has the public and the private associated with it. Private is it's only accessible from within the same class. Declared all instance variables private by default, make the methods public. Declare private methods if they are not part of the class contract and are just internal implementation helpers. We're just going to use it for implementing inside of the class. And a class, let's see, that's designated as public. You're never going to have a private class. You could have a private class. But what's the sense of that? Well, you know what? Math is private. You're just going to run the methods in there. Math dot absolute value. Math dot, because you're using it sort of like a function. If you think about it, you're never going to you're not going to make any instances of it. You can't make an instance of a private class out in main. You're going to use it at the class level. Everything's going to be static inside of it. If you make a private class and you try to make an instance of it, you're going to get a compiler error. So we can put private classes inside of private classes. We can make a hierarchy of nested classes inside of classes. That's private. It's the same way as making the data private inside of the class. No effect. It can be used inside of the class. We make an instance of that class. We can't run those private anything. So if we have a private class inside of the private method or public method or something, not going to be runnable, not going to be usable. So a lot of people would make internal methods private because they're not going to want them being used. So they're helper methods that are going to be used to calculate an area or something. Make it private. Make the class private when you're not going to make any instances of it, you're not going to do anything with it. By default, everything's public at the class level because it makes it non-functional if it's not. So public means that any other class can use it, can use this class definition. So the name of the public class must match the file name as we saw before, or the file can only have one public class inside of it. If you put it all inside of one class, you'll get separate .class files out of it because the compiler will correct you and actually create the separate files for you. So we also have this keyword protected. Protected variables or methods can only be accessed by methods within the class. So classes within the same package and classes within the same subclasses. So if it's protected, that means if you're in the same package, you're good. If you're in the same inheritance line, you're good. Which means if you're extending, but not interfaced. Only through inheritance and through package, so, or subclassing, I should say.
But that is same with the private ones, right?
Correct. No, private is private. If you inherit one class from another class and you have private in there, not accessible through inheritance. Protected is, though. Private is private. It cannot be used anything outside of that class implementation. Protected is kind of a way of violating the private. Say, hey, you know what? Main, it's still private. But if you belong to my same hierarchy or you're in my same package, okay.
But it is not accessible through instance of the class.
No, no. Default. Default visibility. Actually, there's a keyword default. And there's default visibility methods. If you don't put anything in here, you have accessibility at the default levels. Default visibility indicates that the variable or the method can be accessed by methods within the class and within the classes of the same package of basically being public in that aspect. Variables or methods have default visibility if a modifier is omitted. Leave out the modifier, you're going to get default. Default says, okay, you're public within the same class level and within the same package level. You want something set past that, you're going to need to set it. Otherwise, you don't have any default value. So it's going to be private. So private is very common. Use this at first choice. When in doubt, make it private. Public is common for methods and constructors. Second choice. Protected, usually for instances, variables only. Moderately used. You're going to use it when you're going to break a rule, when you have to make something work. You want this inherited class to touch the data member, to change it for something, then make it protected. Don't make it public. So, because if you think about object responsibilities, each object is supposed to be responsible for its own data members. So if I have an object called person and I make an employee from that, person should be setting its own name and address and telephone number and social security number. An employee can take that information in the constructor and pass it back to the person to set it. But a lot of people don't want to do that. Instead, they'll make the person stuff protected instead of private, and then they'll change it inside of an employee, which breaks down the inheritance. It causes problems because this person might be setting the information, this object called employee might be setting the information differently than this one over here called staff, and that one over there called something else. So if you let each base object be responsible for its setting and getting of its own memory and its own data states and stuff, then you don't have people telling other people what to do. And every person's in control of it, of their self, essentially. It's like me telling one of you guys out here, you know, your name's not whatever your name is, your name's now Bob. Like, what right do I have to do that? Well, if you make your data protected and you let me inherit from you, then I can tell you what your name's going to be. But normally you don't want your name changed like that. So if you make it private, I can change my name when I feel like changing my name. So you go down to the courthouse and you change your name if you want to change your name. But you're not going to tell, someone else is not going to tell you to change your name. That's the problem you get when you make things protected. You're going to have other objects changing your name for you. When, what right do they have to do that? Oh, you gave them a right. You said, okay, you can do it. So, but the general public can't, but you can. Okay, so anyway, that's what that means. Visibility summary here. You don't have to worry about this. I'm not going to show you a chart like this on the exam and say, which one of these is true? No. It's just a summary. It can be kind of hairy. If you just remember the fundamentals on what it is you're looking at. You only got public, private, and protected. So the default is rarely used. And you leave it out and you get default. So modifiers, here's some other ones you may not necessarily be remembering. We actually went over all of these in the last weekend of the class. Final. So for a variable, it cannot be changed. It's constant. It cannot be changed. It's final. After instantiation. Widely used to make immutable classes. You make the class final. Why do you want to do that? Well, because you want it, but you don't want it changed. Don't change the concept of an area. Don't change the concept of a shape. I'd make shape final. Shape is a shape. Don't turn the shape into a boat or to a car. Don't let them do that. So then it reinforces the integrity. Variables, classes, everything can be public, private, protected. Everything can be final, synchronized, volatile, transit. All these apply towards all these concepts as well. For a class, you cannot be subclassed. I've got a definition of a square. I don't know if I'd make a shape final, because then I wouldn't be able to make a square from it. But once I have the square, I'm going to make the square final. Why do I want like a rectangle square? No, I want to require them to make a rectangle. I don't want them to be subclassing a square. In Android, we have a bunch of classes that are like activity. You can subclass activity, excuse me, but it's final. You can't make a different type of activity. It's restricted for the implementation of the API. But you can subclass it, but you can't. Yes, you can, actually. That's a bad example. Let me think of another one. Well, in the language, class. You can use class, but you can't make a class from a class. It's a keyword reserved, but it's actually a concept. It's an object type. But that's a bad example, too. Let me think of another one, huh?
Math class.
Math.
That's final?
That's true. Math is final. Yeah. Because you can't make a subclass of math. You can't extend the behavior. You can't do anything with it. It's stuck. Yeah, good. Math is a good example. Yeah. For a method, you can't override it either in a subclass. So you can make a method final. Area of a rectangle is final. And you make a new colored rectangle, solid rectangle or transparent rectangle. You change something about the appearance, but the area is still the area. You can't change that concept. Synchronize sets a lock on the section of the code or the method that's going to be shared with something else. Only one method can access the code at any given time. So if you remember the thread stuff, if you're in the Android class, I gave you the thread stuff. I'm going to give you a little bit more synchronized stuff in this class, actually. This is one of our advanced topics after lunch. But long story short, going back to what I said about the dynamic memory, if we only have one copy of something in memory and everybody's using it, Synchronize just puts a lock on it. Means if this current running activity is using that, nobody else can use it. So everybody waits. Concurrency, yeah. It's for interprocess communication and concurrency control. But it's interesting because we don't really have, well, we have threads running, but when we put Synchronize on it, because we only have one hello world in memory, or one something in memory, we don't have multiple copies of it, we can control the access to it. So it actually makes thread processing, thread programming, I should say, in Java extremely easy compared to other languages. Because other languages, you got multiple copies of everything out there. You only have one if you're using it efficiently in Java. Volatile guarantees other threads see changes to variables, which means if something is updated, it's resynced. So you've got the synchronization going on. Transient, well, variables are not stored in serial objects. They're stored in shared memory. So, and then native indicates that the method is implemented using C or C++, actually. It's native, it's not Java. So what was Java's actually written in C, which is kind of funny. You think, oh, we have to assembly language. To make a compiler, you're running java.exe and javac.exe. It's a C++ compiled program. It's called a compiler. There's a Java version of it, but you're running it, something that's making Java code for you, which is kind of interesting as a concept. That makes it native. It's not part of the language, it's native. It's part of the compiler, part of the assembly. So Java supports 3 different types of comments. Kind of review again, you know, for those people who need a lot of review. This here, the double asterisk, is for the Java docs. Java docs, as I mentioned before, are automatically created by going Java doc space and then the name of the file. Pulls through and parses out the Java docs that are in there. I gave you some Java docs stuff last time. No Java doc questions on the exam, so you don't have to worry about that. So I'm going to kind of skip through this here, and this here is going to have the @author, @version, @parameter, stuff like that. So I'm going to skip the Java doc stuff because there's no questions on it, and I gave this stuff. This is review, so I'm going to give that stuff to you. Overloading is what we've been looking at. Overriding, what we've been looking at in terms of methods and inheritance. So you can have multiple different methods or constructors with the same name. It's another concept of the overloading. So, no questions on best practices, although there are some questions on the inheritance concept. When you see the keyword extends, you know you're inheriting. And hopefully at this point you have a good understanding of what inheritance means in the language itself. So now what I'm going to do is stop this lecture, start a new one on assignments, and then we'll go to lunch after that. Because some people might be working on assignments. I mean, the assignments for the class, not assignment expressions, but assignments. Because some people are probably still finishing it up. So let me stop this so I can segregate the topics a little